platform, the easier is for you to debug your program. Okay, so I don't restrict what you must write, but the end goal is that you have a utility program that you can take with you to run to check the platform, whatever that platform is. Okay, so that is the. If you have questions, or how should I report things? It's the end goal is for you yourself knowing that how exceptions is handled on that platform, right? So the exception handling that needs to be comprehensive, right? Overflow, underflow, underflow is soft landing, and how the positive zero, sign zero being handled, how the propagation of different rules being handled. Those are of interest to anybody implementing a software on the platform. Okay. And my computer is finally back. I think that I don't know what's the day that will happen when the natural language can go into directly computer programs. Okay, I believe that day may not be too far away. Okay, so that will eliminate the first level of programmer. Okay, so that's just like labor. Okay, robotics will eliminate the first layer of labor. It's just the way it is. Okay, we can discuss about the ethical question, the political concerns, or whatsoever. Okay, but it's going to happen. Okay, if you are a business person, hiring a programmer, if that cost is more than you buy a license to use a naturally generated program, the machine-generated program, then the programmer won't be hired. Period. Okay, so this is for sure. There's ethical and political and all these complications. Okay, but the invisible hands. Okay, whatever is the most efficient way of doing things in the commercial world, it will be adopted. Okay, so the next level of programmer that we are hopefully this class will prepare for you is that how will you be able to comprehensively verify, okay, not only test, verify that what you do is correct. Okay. Okay, almost come back. He's doing my funny things. What are you doing? I have decided not to complain about Microsoft anymore after Gates Foundation have done such a wonderful thing for humankind. Okay, so I stopped complaining. I vow not to complain anymore, although every time I want to. Yes, okay. Finally. So Bill Gates not only donates 95% of his assets, he's encouraging all the other billionaires to do the same thing. Good guy. And he's looking at all the problems that should be looking at by government, but still. He's doing very good thing in the Gates Foundations. Ooh. Look up. Why are you so okay. So one of my technical dreams, I think that the almost being achieved, is that every kid in the world can have a network computer, and they can afford it. Okay, I think that's almost achieved, and that for sure there's more thing to do. That computer need to be able to educate them. Okay, so no brain is wasted. Okay. Now we're almost getting there. We're almost getting there. So we need a very good software to run it, okay? So today we are going to go finish the integration. Okay, that's the last thing that doesn't work. Okay, that's fine. You can use this, okay? So we explained when they call integration, it's called quadrature, okay? It's called quadrature. So it's the same thing we do as the differentiations. We would like to integrate, right? Get an answer for the integration or interpolations or getting the average behavior on a binary system. Okay, so the first thing we do is discretize, okay? Because we have, we cannot, another way will be doing symbolically, okay, which is not possible for many problems. So for binary system to deal with this, right, the first thing we do is to discretize the systems. So then we approximate your integration with this summation form, which is strictly the definition of integration. Now comes the question, where should I sample, right? I need a sample of your function knowing how to integrate the area. And what should be the weight that apply to each sample, okay? So now this is the remaining question, okay? How do I determine, how do I do the where to sample? And when I sample that point, how much weight I should put on that sampling, okay? So that's the first thing we can do is that, okay, to make the math cleaner, let's assume that you have done this before, that you can shift and normalize. Remember, these will carry a constant term in integration. Okay, when you normalize, when the fx have a goal for change of variables, that you can do shift and normalize. This will cause a constant out of the integration. Okay, but let's assume we have done that. Okay, we have done that. So it's a simple. You have a originally fx, right? You write a explan. That's g of x, right? And you use this one, change your variables, to shift and normalize that the integration is from -1 to 1. Okay, this is always part. This is a linear x can always achieve that. A linear x of change of variables will cause a constant out of the integration. But let's assume we have done that. Okay, assume we have done that so that the mass form is cleaner. Okay, so the mass form is cleaner. So the possible choices is a lot of them you know, and I showed it briefly last time to you, okay? But let me show you what is the general principle to do the least effort and get the most accuracy, right? Just like when we learn from differentiation, right? A local analysis of differentiations, you can have the sampling, and you would not like to do a lot of sampling for sure, improve the accuracy. But sampling takes effort, right? Sampling takes effort, so that so you want to find what is the minimal age, a minimal approximation function that you get the desirable accuracy. In that exercise, for sure, it's much better anyway, because you have an idea about the error. You know the lower bound of the error that provides you a way to check and verify your results. Okay, let me say that again. Okay, this is a core things I need to train you for, right? You want to spend the least effort to get the most accurate results, both in your spatial discretizations or in the order of your approximation. Okay, least effort, most accurate results. Simultaneously, you use a combination of that to write an error estimation. And that will help you to verify whatever you compute. Okay, because now it's not a blind coding. It is you always sit on top knowing what kind of error I'm dealing with. If I reduce the discretization to be half, what am I dealing with? If I increase the order of approximation, what am I dealing with? If I compare the different orders or different discretizations, what they should give me. Okay, these provide you with all the verification tools that you can have. Okay, so here is no surprise. The first one is one you have used. Okay, that the called rectangular. You sample the beginning point and integrate over the period. Okay, it's a very simple rectangular. Trapezoid. Okay, you say okay, but that's not fair, right? I sample at the two end and use the average, right, as the integration sample. Midpoint is something I want to do less effort. So how about I just sample instead of at the rectangle at the left or at the right, I sample in the middle. Okay, all these are below second order. Okay, a method. Okay, I'll show you how the approximation can be written down, again by Taylor series, and tell you the general principles to generate higher levels, higher orders approximation. Okay. Simpson rule is probably something you have seen in the calculus. Okay, so in the basic calculus, it tells you that if you use Simpson rule, okay, I'll tell you how the Simpson rule is derived. You put a midpoint in the left and right boundary, and you assign different weightings. Okay, so this is it needs to be exactly 1/6 and 4/6 and 1/6, so that it is the most accurate result. Okay, I'll show you why. Okay, so this is a Simpson rule, but you do spend 3 sampling points. Okay, and it's because of this Carl Gauss. Okay, he's think about Simpson rule and say, oh, but that's waste of effort. I only need 2 points sampling, and I can achieve the same thing. Okay, I'll tell you the thoughts of how Carl Gauss derived that as well. Okay, so you can do 2 points, but those are 2 special points. Points chosen carefully where it is and how it's weighted, that you can achieve the fourth order. Okay, and for sure with the same principle, there are all the. If you give me 3 points, what are the weights? You can do even higher order. Okay, so you can generalize this using this Gaussian quadrature. Okay, then you can use the least number of sampling to achieve the highest order. Okay, the highest order, and you can compare different orders to estimate your error. Okay, let me show you the derivation. Okay, show the derivations. Okay, before I do that, okay, let's see a very simple example. Say you have a cubic function. Okay, a cubic functions, and if you use the blue line, okay, it's the real function. Okay, this is a real function. Blue line is a real function. Okay, and it should, because it's a polynomial, the closed form solution tell you the answer is 2/3. Okay, so trapezoid rule. Okay, trapezoid rule is the orange one, right? Trapezoid rule is I estimate here and there, right? Average the result. For this particular example, trapezoid rule performed horribly, right? Because what happened in between the function is not sampled, right? So this is a horrible result. If your function is a monotonic function, then you probably imagine the trapezoid rule may not be doing too bad, okay? But something that it changed a lot within the left and right boundary, then trapezoid rule only estimating the error of the trapezoidal area, then it gives you very inaccurate results. Okay. So, but since this is only a third order cubical, okay, cubic functions, okay. So if you use Simpson rule, fourth order, or the 2-point Gaussian, you get the exact answer. Okay, not surprising, okay, because those methods are fourth order accurate, and for a third order function that you integrate out, you will integrate it become fourth order. So you capture all the fourth order things by a fourth order approximation. Okay, so that both the fourth order one will give you the exact answer. Okay, for Simpson, I just you can see how the magic is done, right? So how this number, right, play into the exact number of 2/3. Okay, but it's not a big surprise. Okay, it's that the cubic function integrate into fourth order. I use a fourth order approximation. I should capture everything. Capture everything. Okay. Okay. Let's see how all these quadrature can be derived. Okay. Derived. Okay. So back to when we do the differentiation, we do Taylor analysis, right? Taylor expansions. So we say that I would like to capture the function behavior according to the Taylor expansion. Okay, you can see immediately I omit all the odd order terms because of the normalization, right? I normalize it, right? So all the odd order term between -1 and 1 will not contribute anything to your integration. Okay, so there's only, so this is different from the differentiations that in integration, if you do shift and normalization, all the odd order terms, odd function will drop out. Okay, just integrating of an odd function across -1 and 1 for sure give you 0. Okay, they give you 0. Okay, so the zeroth order term is easy. Okay, zero order term directly tell you, right? In this, right, it is the zero order term if your fx is nothing but a constant, right? So it tells you that if you want to integrate a constant function correctly, okay, the summation of your weighting has to be 1. Okay, that's not surprise, right? A constant, right? If your weighting don't add up to 1, then you won't be able to capture the constant function correctly. Okay, this is not strange. Okay, not strange at all. Next one is a little bit more tricky. Okay, more tricky. Now I'm asking, okay, if I have the constraint of all the weighting, sum is 1. I capture the A0. In order to capture the quadratic terms correctly, okay, quadratic term correctly to the 4th order accuracy, okay, then what should I do about the weighting and the location of things, okay, and the location where I sample it? So let me use here, okay, this because fx now is a quadratic function, right? So the integration is nothing but this symbolic form, okay? So that's simple, okay? And if you sample at, right, the xk plus 1 and k, then this is the exact form symbolically, right? So I'm integrating a quadratic function, right? And that will be my answer, okay? If I do it exactly, okay? Let's check whether Simpson rule have achieved this, okay? So Simpson rule tell us that this is a sampling, right? So let's do the Taylor expansion for all these fx, okay? Taylor expansion of all these x, and because fx is known, I actually know what is the expansion, right? The expansion is exact, right? Because I know fx now, it's my quadratic function. Very simple, okay? So let's expand that, right? This is the beginning point, expansion on the midpoint, expansion on the right, right? You sum them up, grouping your terms, you'll find that it indeed achieve that thing, right? So if you just, let's check fx, okay? Fx for sure, fxk, it's 1, 6, 4, 6, and 1, 6. That for sure is 1, okay? Sure, okay? So second term, I have this contribution and this contribution, right? So it adds up to hk over 2 of my second derivative. For sure here is 2a0. Okay? I know what is the, I just want to integrate the quadratic function correctly, right? And then you can verify that this is also correct, right? So this is a term that collect your second order derivative, okay, second order derivative. And then you get, okay, exactly as what you should get, right, on the symbolic function. No surprise, okay? Now, if I ask the question, for the 4th order, if I only give you 2 points, I only allow you, we check, okay, just use the Simpson rule. Simpson rule, it's integrating the second order correctly, okay, that we know already, okay? So here, that I'm constraining you that I only allow you to do 2 sampling points, okay? Let me assume that you do the sampling point at xk plus L1 and sk plus L2, okay? So this is my assumption, okay? So between that xk and xk plus 1, there will be 2 points I sample, right, with 2 unknowns, right? 2 unknowns, okay? And there are the weighting of W1 and W2, 2 weighting, okay? So I can expand it with the Taylor function. I want to match the conditions where my 4 degree of freedom, L1, L2, and W1, W2, right? Four unknowns so that we map to the way that they integrate a quadratic function symbolically exactly. Okay? Let me see. I'm saying I'm only willing to do 2 sampling, right? 2 sampling at 2 locations. I don't know yet. I give the weighting for that. Okay. The goal is to achieve that if the function, if the fx is a0 plus a2 x squared, the integration will be symbolically exact. Right? So, and you take a step back. This is definitely achievable, right? Right? I only have 3 constraints, and I have 4 variables to choose. Right? Consider our Simpson rule matching, right? Simpson rule matching, right? How we match this coefficient, and this coefficient, right? To be the 4th order accurate. 3 coefficient after the expansion to match, then it will be matching the quadratic function exactly. So now, if I tell you I have 2 arbitrary points with 2 weightings I need to do, I be able to estimate the integration of a quadratic function symbolically exactly. Right? No hand waving whatsoever. Okay, saving your time for your algebra, you'll find, okay, in order to match, you expand, do the Taylor expansions around L1 and L2, okay, and expand it out, match the coefficient, this is the constraint. Okay. If you compare what I just did for Simpson rule, okay, this is exactly what I did, okay, exactly what I did. And now I'm using a more generalized form, like the one I use the generalized 2-point differentiation. The derivation actually very similar. Right? I say if I do the 3-point, 2-point differentiations, I can do write down my equations. But if I give you 3 sampling, what is the best accuracy you can get? You can write down that H1, H2, okay, that thing we have gone through, and find out your higher order estimation for the differentiation. Here's the same, okay? I now give you 2 internal points, okay? I want to match the highest order. Okay, so this is a constraint I get. Okay, I can. So there are infinite choices. Okay, there are actually infinite choices that will be 2 sampling points and 4th order correct. Okay, but let's be fair. Let's say, okay, a popular choice is either L1 and L2 is of equal distance from the boundary, or you constrain the weighting to be half and half. Right? So these are you need the additional constraint to get a finite thing. Okay? What Karl Gauss did is that he constrained your x w1 equal to half. Okay, he constrained. Right. He put on the additional constraint, solved it. Okay, and this is the solution. Okay, so if you look at, I need one more constraint, right? The 4 variables, 3 constraint. Okay, Karl Gauss says, okay, let me just constrain W1 equal to W2, additional constraint. Okay, so the 2 sampling point, because they're arbitrary, I can choose it arbitrary now. How about I choose the weighting to be the same? Okay, so additional, you put that constraint in. You can solve that very simple, algebraic equations. You come up with your 2 points Gaussian integration. Nothing fancy, okay? With knowing this procedure, okay, if I give you 3 points, okay, to get my 6th order, okay, you can do exactly the same thing, okay? You will constrain saying that I would like my weighting to be of some form, okay, and then you can derive where you should sample, what should be the exact weighting function, weighting number. Okay, you can extend this to arbitrary order. Okay, the more sampling you have, the more accurate approximation you can make, higher order approximation you can make. Okay, okay. So this is the solution of that, and you can check. Okay, if I substitute the solutions, do the Taylor expansion. Okay, Taylor expansion, you will find after some relatively lengthy algebra, okay, exact functions symbolically. Exact functions of your quadratic integration. Okay, this algebra is a little bit lengthy, but not hard at all. Okay, just matching terms, you'll find out that for sure I solved it, right? So it is correct. Okay, it is correct. Okay, any questions? Tell you the principle. I won't bother you with the algebra and things. Any question about this procedure? This procedure will happen 2 more times in this class, okay? 2 more times in this class. When I do the spline curve, okay, it will happen is how should I choose my spline curve to smoothen a geometry, okay? Exactly the same principle, okay? When I'm dealing with my ordinary differential equations, what should be my time sampling, okay? Time sampling to best approximate under the given accuracy. The same thing will happen again, okay? I'm assuming a Taylor series, and then I match the coefficient, okay? Solve what is the choice of coefficients that can give me the highest order of approximation. Okay? The general procedure actually apply for many other problems, okay? So if you know the general procedure, take a step back. Why do I need to do this? Why am I interested in doing this?
You don't know the ground truth.
What? We don't know the ground truth. And?
Yeah, like whatever you're integrating in the general.
Yeah, fx is generally not like your a0 plus a2 x squared, so it can be a very complicated function. Maybe even this x containing 1,000 factors, like you're calculating the Dow Jones index, right? This got like 5,000 variable in here, change all the different times. So you can, there's fx can be sampled, but you don't know its behavior at all, right? So the goal of doing this is because I would like to use the least sampling to know the highest order of accuracy. By doing this process, I also have an idea what's the error I'm dealing with. Okay? Without knowing the error you're dealing with, many times, I think I see even now 2 codes, that your calculation is wrong, not because your approximation is wrong. It's your code is wrong. You have a bug there, right? Originally it should be divided. You somehow in your code is become multiplication. Okay, so if you have an idea about what kind of error you are dealing with, then you can, even you have a code bug, right? Not because of approximation, okay? You have a bug in your code. You have a way to estimate, but this is not the error I should be getting. Okay, then you can go back to your code. Maybe you have a bug in your code. Totally possible. It can be a bug in your functions. That's also possible. Okay, but with that understanding of what's the error you're dealing with is the number 1 principle for any verifiability. Okay, if you don't know what's the error, okay, if you cannot write down an error estimator, then the only thing you can hope for to verifiability is by faith. Okay. There's really nothing else you can do. If you cannot write down an error estimation, then people ask you, how accurate is this? Your only answer can be, okay, I believe it is correct. Okay? And for complex problem, usually not acceptable. Okay? Not acceptable. Okay? So, So this reflects just that this is how the HP adaptivity, right? H adaptivity chose more sampling points or equivalently smaller H, right? H adaptivity is just choosing more sampling points to make the H, effective H smaller. P adaptivity means using the higher different order of approximations, right? Approximation from the interactions of the two that you can find, okay, two things you can do: estimating the error. Second, how you should choose HK in the first place, right? You can have a wishful thinking. You can arbitrarily choose HK, but no, okay, you choose HK implies your error, right? And many times during the trial of choosing HK, last time in the lecture, for 3D problems, is 500 times, 1,000 times more expensive computational problem. You can't, okay? Most of the time, but just by trying out your discretizations in realistic 3D problem like weather, forecast, you can't do it, okay? You have to use other way to estimate the error and choose the acceptable HK. And that comes with all the general principle, right, of HP adaptivity. I can know how good is my approximations by trying out different order of approximation, by trying out perturbation to the H, then I can know what is the error, okay? Or I can get an estimate of the error. To make your things, I would like you to do this actually, okay? Since you have do the differentiations, okay, already, okay? So let's go for a coding exercise, okay? That's integrating that function, okay? This is a monotonic function now, okay? So this is a monotonic function. So it's your rectangle and trapezoid will not do as bad as the cubic function you have seen. But let's see what you can get, okay? More interestingly, I would like to observe how the error in a more well-behaved function, okay, this is a well-behaved function, monotonic, okay, but for sure the higher the order, the better approximations. I would like to know that you observe how the error propagates, okay. So let's do that very simple one. That let's try, okay. If you can finish this in 5 minutes, you are great, okay. 10 minutes, you are ready for interview. Okay. Let's try it. Whatever Python or C or what platform you have. Let's try it out. Okay. Write it in the way that your fx can be general, okay? Don't hard code your fx into the function. At least call a function for the evaluation of fx. And I'll show you the magic thing you can do that you always want to do whenever it was equal to. Yes, rectangle is just use these functions. Right? So, okay. If you have, I can copy down the fx. Fx is H here, it's 2, right? From -1 to 1. H is the interval length of what you're integrating. So I'm integrating from -1 to 1, so H is 2. X is wherever you sample, right? Between -1 and 1. So in the first one, it's just that xk is minus 1. Xk plus 1 is 1. Right? For the simple problem that we're integrating. I'll give you 1 more minute, whether you can finish or not. I'm really sorry, I have an important message to tell you out of this exercise. Okay, if you didn't finish, that's okay. Okay, that you can finish in the next today. Okay, that'll be the training of being able to do a instantaneous programming. It's as important as you being able to do systematic programming. Okay, that's why I force you, knowing that this probably the hacker practice is longer than the average programmer can do. Okay. That if you can code what is required in this one, it should be more than 5 minutes, okay? But this is the ability to be able to write down program very fast. It's probably slightly less important, but it's also a very important skill in programming. Imagining when you are debugging, okay? Most of the time when you're debugging, you're writing small test program on the side to see how you trace a code, right? You can use a debugger to trace a variable, that's fine too, okay? But most of the time, when you're doing debugging, that you are writing test code, okay, to test different parts that you think can be the error, okay? And because the variables human can handle is small, that also means you need to be able to write code fast, okay, or else you forgot what you're doing, okay, because you are. So during debugging, this very fast code, very fast programming, is also important, okay. So I force you to say, oh, this is not fair, unfair requirement for me, okay. I hope that eventually you can go into that stage during debugging, you can write very fast task code, okay, be able to help you debug. Let me strengthen this concept, okay. What you are doing, Ito Han asked a very good question, okay. It's something that's what I'm doing in this very fast programming. Most of the time, I'm translating what is symbolic to numeric, right? Numerical. So, or in even more general terms, you are translating a human language to whatever computer language that is. That's what you're doing, okay? For the very fast programming. If you are given 2 days, you can for sure modularize it, test it, all these beautiful things, okay? That is necessary, okay? Just like any translation between two languages, there are two things you need to learn, right? You need to learn how to translate it, like you're translating a book. You have all the time to do the very good translation, dictionary, wiki, and do a good translation. That's important, okay? It is also very important for on-site translation. Okay, not only because it's necessary for speeches and things, right? There are times that you are a translator, you need to be able to do on-site. That's what I will force you trying to do, okay? And feel comfortable with it, okay? You are a comfortable programmer, you need that ability, especially in debugging. Okay, you need to be able to write a small task code fast, okay? Just almost like on-site translation, okay? And I am a semi-professional translator between Chinese and English. I do all the big speech translations on-site. And let me tell you the secret. The secret is practice. Okay, so I'm forcing you to do this. Okay, just like any translation. Okay, so if you're not comfortable, okay, you never receive this kind of real-time programming training. Okay, this class is a good time. Okay, that you can try to get it as fast as possible. Okay, on the other hand, I'm training you how to do modular systematic programming as well. Okay, but that very fast programming, like on-site translation, is a precious ability you can have for debugging. Okay, so when I force you to do this, okay, let's try. Okay, if you don't have that, if you're not comfortable to do very fast coding yet, okay, hopefully at the end of this semester, each time try. Okay, I was not born as a great translator, but after a lot of practice, I become pretty good. Okay, so is this. Okay. So it's this, okay? So comfortable with writing this, okay? So if you have finished this, you have the freedom of doing this, okay? You probably have believe that a Gaussian function, a normal Gaussian function, that every time they tell you the bounds of whatever, right, you have to believe that, right? Because it's not symbolically doable, okay? Change your fx to be the Gaussian function. You'll finally see, oh, now I have a way to evaluate my Gaussian function. Okay, instead of believing that 97, 2 sigma, 3 sigma, it's whatever that percentage. Okay, now with this function, you can do it very fast. Okay, very fast. And the difference between these two tell you, right, how accurate is the method. Simultaneously, what is outside of your functions to evaluate your error. Difference between these two, okay? Difference between all the different methods, the error you tabulate, okay? Okay, that'll be the end of the lectures. You're supposed to give me either by email or by hand in today, okay? The second homework, okay?
Yes, I was going to ask you.